The second talk is from Bo from Pinterest. He actually came the last meetup here, last meetup at Facebook. So welcome him back.
Thank you, Sing. Hello, everyone. I'm Liu Bo from Pinterest. I'm working with the serving systems team there. Today, I'm going to present Rocksplicator, which is an open source library for replicating and managing embedded RocksDB for online stateful service. The first question I want to address is why we chose RocksDB. We adopted RocksDB about 2 years back. The short answer for this question is that we had a set of new requirements which could not be met by our existing storage system. So, and RocksDB could help us to solve those problems. So that's the reason. And let's look at those requirements. The first one is we want to achieve low latency because all of our new services are like for online serving. So for each request, there will be a real user waiting for the response from our system. So it has to be fast. And more importantly, our systems are usually at the bottom layer of the whole Pinterest core stack. So that means a single client request usually need to fan out to tens, even hundreds of requests to our system. So our system latency is very critical to the client perceived latency. The last requirement is that for all of our new system, we need to fulfill a read request, we need to process a large amount of data. But usually the returned response is very small. So for this, it will be very efficient if we could collocate application logic with data. The last requirement was that to achieve lower read latency, we usually need to incrementally organize data at the right time. And even sometimes we need to do that with a async background threads. So with this requirement, that means we will need an embedded storage engine. So it turned out that that was a good decision to adopt it. So how is RocksDB at Pinterest today? Today, we have 5 different RocksDB-based online systems at Pinterest. And we are running nearly 20 clusters and over 1,600 hosts in production. And all these systems process like tens of petabyte data per day. And all these numbers are still increasing. And for all these services we are building, they share some common patterns. The first thing is data is sharded and replicated. The data is just too big to fit into one host, so we have to shard it. And to achieve high availability and scalability, we need to replicate data. So typically in our system, each shard has 3 replicas. With this, if we want to build a system with this property, that will have some non-trivial tasks you need to solve. For example, since your data is sharded, you need to route traffic, route your request to the proper destination host. For example, for a read, you have 3 replicas. You can send your read to any place, but usually we prefer the local replica to the remote replicas. But what if the local replica is slow? Then we need to reroute it to remote replicas. For write, you have no choice. You need to figure out where the master is and then send the request there. Since we need to replicate data, so we need some kind of a tool or library to do the replication for us. Since this is for online service, we need the library to be able to achieve very low replicating latency. The second common pattern is that we are running our service on top of AWS, and AWS is on top of commodity hardware. So it's inevitable to have that host. So we will need to replace, if that host is detected, we need to replace it with a new one. And also we want to minimize the client impact. Since all of our services are stateful service, you need to copy data around before you can add a new host. So it's also not a trivial task. The next thing is we need to be able to expand or shrink cluster capacity to adapt to the load change. And also this needs to be done without any downtime. Lastly, for some of our applications, we need to do bulk upload. So some of our clients, they want to generate data through offline MapReduce job. And so we write some tools for them so that they can easily dump their MapReduce output data into SAT files directly. And those files can be understood by RocksDB, so we can just add those files directly into our system and serve it then from there. And some of our applications are hosting critical data, so we need to do periodically data backup, though we have 3 replicas in the system. As we can see, all these common patterns, all these problems, they are non-trivial tasks and they are commonly shared. So we were thinking, is it possible to build some commonly shared library which can be used across the board? This is actually what we did. So we built an open source Rocksplicator. This is common system picture of all of our service, and the green component are included in the open source library, Rocksplicator. And the black component are either third-party library or third-party system. And the red component is application-specific logic. So if today you want to build a new service, you just need to work on the red component and reuse everything else. You don't need to handle anything about, for example, cluster management for stateful service. And also, you don't need to care about data replication and so on. We will go through how does this system work. First, when you create a new cluster, you just use admin tool to generate the cluster config and push it to the Zookeeper. This config will include information like the IP and the port for each host in the cluster, and it will also include the shard map and also the role of each shard. And also, if it is a for each slave shard, you need to specify where should you replicate data from. Usually it's an IP and port for an upstream server. Then when a service process first start, on this picture, the rectangle on the left bottom part is a process. When it first starts, it will load the config, and then it will parse it. It's not difficult to figure out what shard should be hosted locally. Then based on this information, it will create or open an existing local RocksDB instance. Then it will parse those RocksDB handlers to the Replicator Core. Then the Replicator Core will do the data replication for us. Basically, it will get the update from local master and send it to remote slave. And in the meantime, it will get an update from remote master and apply it to local slave. For admin tool, we can also use it for cluster management through the admin API. The admin API basically provides a set of primitive interface, and the admin tool make use of them to drive those cluster management tasks. That includes, for example, replace that host, expand the cluster, or moving shards from this host to that host to balance the load across cluster. I will take replacing a dead host as an example to give you a sense how we do cluster management. If there's dead host in the system, reader will still succeed because we have 2 other replicas. Our routing library will detect that and route your traffic to the good host. But for write, if the write destination is to the dead host, we have no choice. The write has to fail. So we want to replace that host as soon as possible. The first step we are going to do is to terminate the dead host. Because we are running on AWS, it's possible that a dead host could come back again. It sounds unreasonable, I don't know. So we do this as the first step because we just want to avoid split brain problem. The second step is to remove the dead host from the cluster config and then push the new config to Zookeeper. And the Zookeeper will propagate this update to every host in the cluster and also to every client. The third step is to promote masters for shard with slaves only. Because since we have removed that host, so we will have some shards in the system which has like only 2 slave replicas in the whole cluster. So we will check those 2 slave replicas to see through the admin API. Say, what's your largest what is your latest sequence number? And then we will promote the one with the larger latest sequence number as the new master, and make the other slave to replicate from this master. So once the first 3 steps are finished, then the whole system will be back to normal. I mean, it will be able to serve all read request and all write request. Typically, these 3 steps will take like tenths of seconds to finish. The 4th step is to create a new host in the same availability zone as that host. Availability zone is a AWS concept. If you don't, if you are not using AWS, you can imagine it's like some kind of like a region or a building within a data center. Typically, we will put 1 replica. We will use 3 availability zone and put 1 replica in in each of them to achieve higher availability. So we will create a new host in the same availability zone as that host. The next step, we want to add that new host to the cluster. What does that mean? Since before doing that, we will have some shards which have only 2 replicas, 1 master and 1 slave. So we want to create a second slave replica and put it on the new host. What we do is we will request the master replica again through the admin API to back up to HDFS. And then we restore the data from HDFS to the new host. And then after that, we will request the new host to replicate data from the master. One thing I want to highlight, I want to note is that for this step, we do it in small steps. Let's say if this new host needs to host 40 shards, we will do the first shard first and commit this change to the config file, and then do that for the second shard, and then commit the change again. So we do it in small steps. Lastly, we need to rebalance master distribution because the new host now has only slave shards, and typically to host a master shard, you need to spend more CPU or whole system resource. So we want to balance that. So we will move some master row from other hosts to this new host. Okay, so we have discussed how we do data replication at a high level and also how we do cluster management. Next, I will discuss how does the application logic interact with the library. Let's say if you want to write a application logic, if you want to read or write to a shard, what you need to do is just query the library to get a DB handler through a getDB API. And then once you get the handler to RocksDB, you can just use that handler to talk directly to your local RocksDB. Next, I will get into more details about the Replication Core. There are some design decisions we made. The first one is we want the replicator to support async replications only. So first of all of our applications are okay with async replication. Secondly, with this decision, we don't need to build any complicated consensus algorithm, which is usually requires a lot of effort to make it 100% correct and performant. Next decision was that we want to make this library be able to replicate multiple RocksDB instances in one process. Because typically a single server process needs to host multiple shards, and we usually use one RocksDB instance as a shard. And we want to assign replication role to RocksDB instance level instead of host level or process level, because with this we can mix master and slave together with on a single host, so that we can balance the load across every host in a cluster, so that we can make full use of the hardware resource. The fourth decision was that we want to make the core very simple. So we designed to make it work reactively. It just provides 2 API, add a DB to do replication, and remove a DB from replication. So it does only one work, do replication. you don't need to decide the whole replication graph or the replication row assignment and so on. Lastly, we want the library to achieve low replication latency because it's for online service. For the implementation, I want to highlight 3 things. The first one is we use RocksDB red hat log sequence number as the global replication sequence number. As a replication system, typically the master shard and the master replica and the slave replica are on different hosts. So we will need some way to let the master to know what exact data the slave is requesting for. So we will need some kind of global replication sequence number, which is unique, which can be used to identify each update. And for RocksDB sequence number, it has very nice property. For example, if you create a new RocksDB instance, its sequence number will start from number 0. If you apply an update to it, the number will be bumped by 1. And another thing is that if you back up your RocksDB and restore it on another host, the sequence number will be preserved. So it's very convenient for us to take advantage of it. So also with this, we don't need to build another layer of persistent log. So it's also minimize the replication, the overhead caused by replication. The next thing is we implement it in C++. We use fully async server, FB Swift server and the client for RPC. The last thing is we use a hybrid approach of for data replication. Typically, there are 2 ways to do two models to do replication: pull-based model and push-based model. For pull-based model, it's easy to implement, but usually its replication latency is higher than push-based model. Push-based model is the other way around. So we use a hybrid approach so that we can achieve both simplicity and also low latency. We will see what that means later. This is the workflow for replicate a local slave. The red component here are in the Replicator Core library. So for each local slave, the library will try to get the latest sequence number for that slave, and then it will send a replicator request to the remote master, asking for updates behind that sequence number. Once it gets back the update, it will apply it to the local slave. This is straightforward. This is on the other end of the network. If you are hosting a local master, usually you will get some replicator request. Once you get a replicator request, the Swift server will pass it to the work thread pool. Then a work thread will try to query the local DB, say, do you have the update after this sequence number? One thing I want to mention is that we don't do this in the Swift IO thread directly. Instead, we do it in a thread pool because RocksDB API call may block the thread. We don't want to block thread in IO thread. We don't want to block IO thread, so we delegate it to a thread pool. If the answer is yes, then the work thread will get the data and send it back to the remote client through the Swift server. This is also straightforward. The tricky thing is, what if the local master does not have the data you need? We will see that first step is the same, still the same. Okay, now you don't have the data, what do? Basically, the work thread will register that replicator request with the internal data structure. And then the work thread will start to work on something else. We don't want work thread to be blocking here because potentially we could have multiple hundreds, several hundreds, or even thousands of concurrent replicator requests. And the number of work thread is usually very small. So if client later apply a new update to the local master, then after applying that data to DB, it will activate, it will notify that internal data structure, then that replicator request will be reactivated. Then another work thread will take on this request and get the data from master and send it all the way back to the client. I want to mention some performance numbers. This is the number I get from a typical production cluster. On this cluster, each host needs to support 1 megabyte per second write from client. And with this load, the P99 latency for replication is 12 milliseconds. The maximum is 60 milliseconds. With a synthetic load of 76 megabytes per second, the number is 106 milliseconds and 224 milliseconds. Besides the system performance, I also want to highlight some developer velocity. With the library we have, we can easily build a production quality counter service in just 1 week. And the system has been open sourced. If you want to try it out, you can just search for Rocksplicator on GitHub. And we have an example counter service in the repo. It demonstrates how to use the library. For the future work, I want to highlight 2 things. The first one is we are building a cluster controller, because currently if we want to do cluster management, for example, replace a hold, we need to get a page by our monitoring system, and then an engineer need to run the admin tool to do all those steps to replace that host. So basically we are building a controller. It will be a standalone process. It will proactively monitor every host in the cluster. And if that host is detected, it will replace it automatically. It can also do some other operation tasks. Besides that, I believe it will also provide a web UI for us to inspect the system status. The next thing I want to highlight is we are building some other replication policies. They will provide stronger guarantees than async replication. Most likely, there will be something like a semi-sync or sync replication as the MySQL server. Thank you very much. Any questions?
Hey, hi.
Hi.
Good to see you. What happens if your replication falls too far behind? I guess it's kind of a loaded question.
That's a good question. So basically, we have monitoring stats for the replication latency. Typically, it's behind 1 second. So if for whatever reason, if we lag behind, we will need to investigate that. So if right now we keep the write-ahead log for 1 hour long, so we set the alert to be 10 minutes. So it happened once in our production system. It's because of some application level logic in the merge operator, which caused the write to be very, very slow. Mm-hmm. So if that happened, we need to figure out. So basically, we set a monitoring, and we set the write-ahead log to be 1 hour. If we want to relax that, we need to change the RocksDB parameter. So typically, the data transfer itself is unlikely to be a problem, because the network usually has much larger bandwidth than RocksDB writes throughput, and yeah.
But you could have a partition for 1 hour or a downtime or something that makes you miss the write-ahead.
Yeah.
I mean, it happens inside our systems, and that's why we have the ability to transfer a snapshot. But so I was wondering if
you mean the network partition?
Yeah. And then when it comes back, it's too far behind, so you have to rebuild it instead of.
Yeah. If that happens, then we probably need to add some function in our admin tool to say, okay, totally abandon the slave replica, and then make the master replica to take a snapshot onto HDFS and then restore it there. It's just like the how we do host replacement.
So yeah, my first question was about like how do you bootstrap a new replica? Mm-hmm. I think this was related, right? So is there like a special way of bootstrapping it through some snapshot, or you just do give me updates since sequence number 0?
Sure. So how we do how we start a new replica? So basically, RocksDB has a feature allow us to do backup. So and for that interface, you can pass it an environment. If you pass it a HDFS environment, it will back the local DB to the HDFS cluster. then we will restore that backup on the new host. Once that is done, you will be behind the original master, right? And then, but as I said, the RocksDB sequence number will be preserved. So you don't have to start from number 0. You just start from whatever the last sequence number in the snapshot, and then you start from there. So usually, since the replicator throughput, because it's for each round trip, it can replicate multiple updates, and it's configurable, so it can be easily catch up.
Okay, I see. And when this new replica becomes ready to serve reads, when the new replica becomes, yeah.
So typically we add this and let the slave replica to replicate from master. Then we will push this change to the config. Then the client will start to request listen and read to this slave. So if you want something like a read after write guarantee, then probably our replicator also provide an API for you to implement this. Basically, when you do a write, we will return you a item or a token, which is just the sequence number for that write, and then it will when you send a read, you can pass that put that in the read request. Then the system will wait for that. And another way to solve that is you can always send a read to master, because all of the hosts in our system are equal, and so you don't. I mean, the load balancing is not an issue here, because every host are hosting 1/3 master and 2/3 of slaves. If you always send the read request to master, actually there's no load balancing issue.
I see. So that it is possible that this new replica is still behind, like let's say far behind than the master one, but it already starts serving reads, if I allow that by configuration.
Yeah.
Okay. In some other questions. So yeah, I think you partially answered to the second question about when do you ACK to client. Like, is there
so currently we only support async replication. That means if the write is committed to the master, then we will return, we will ACK the client immediately.
I see.
So we are building something like semi-sync and full sync replication. In that case, we will wait until at least, for example, X copies of slave has committed the change, then we will ACK the client.
I see. And the last question is about, so is it possible, you said when you elect a new primary, the old one should be terminated, right?
Yeah, the old one should be terminated first.
Yeah, so is it still possible that you somehow timed out waiting for the old one to be terminated and you elect it because you have to elect a new one to support the production, and there are still two alive and they can both start serving writes?
Usually we wait the termination to finish before we proceed to the rest steps. Or usually on the AWS, terminating a host is usually very reliable and fast. I'm not sure about the other platform.
I see. So it's just a kill. Like
yeah, you just kill the old one.
Okay. Thank you.
Mm-hmm.
Hopefully a quick question. So one of your slides said you read a lot of data and then you kind of filter it down to a small amount. Can you talk about what are you doing there? How
sure.
do you get
A typical use case for this is for analytic systems. For example, for our A/B test platform, they need to, for example, query data for more than 1 year. So you need to scan a large amount of data, but the end result we returned is just a set of integer numbers. So this is one case. And another case is for ads and analytics. Sometimes you need to, if you query something like unique impression, for example, the data stored in the DB is actually some rich data structure, for example, heap log, which is much bigger than a single integer. So in that case, you need to scan all those heap log and merge them together and query it for the estimation for the cardinality of the set, and then return just a single number.
Thank you.
Mm-hmm.